Hi viewers, welcome to my class on Mechanics of Materials. In this class, I will be discussing two numerical examples of uniformly tapered bar of rectangular cross section. Let us start with the first example. The problem is to find the change in length of a uniformly tapered bar of rectangular cross section which is 2 meter long and 10 mm thick due to an axial compressive load of 45 kN at its ends. The bar is 70 mm wide at one end and 40 mm at the other end. Young's modulus of elasticity E is 185 kN per mm square. So it is only one section is there, like the cross section is changing uniformly. Thickness is constant and it is 10 mm. Width is changing from 70 to 40 and its length is 2 meter and an axial compressive load 45 kN is acting, and material property Young's modulus is given. Now the load is 45 kN compressive, so minus sign I have kept, so minus 45 into 10 raised to 3 Newton, kilonewton to Newton. Length is 2 meter or 2000 mm and width at one end denoted by A, width at one end is 40 mm, the other end it is 70 mm. Thickness T is 10 mm and Young's modulus is 185 kN per mm square. Kilo conversion is 10 raised to 3, so directly you get 185 into 10 raised to 3 Newton per mm square. Now you already obtained an expression for change in length of a uniformly tapered bar under an axial load. So the formula for that is delta L is equal to PL by T into B minus A into log B by A. So P is a load, so you can substitute a negative sign, minus 45 into 10 raised to 3, length is 2000 mm, thickness is 10 mm, Young's modulus is 185 into 10 raised to 3. B and A, B is 70 mm, A is 40 mm. So here log B by A, log 70 by 40. So it's a direct substitution in the expression. So if you work out, you will get delta L as minus 0.9075 mm. This minus sign indicates that length is decreasing. So since it is only one section, the load you can just substitute the numerical value. It is not compulsory that you should put the negative sign. Since the load is compressive, you know that whatever numerical value you are getting, whatever change in length you are getting is reduction in length. When step bar with a number of sections, you need to consider this compressive as negative and tensile as positive, so that will help us to get the total change in length by just adding all the change in length in the various sections. So in this case the sign convention is not mandatory, it is only up to you to use the sign convention. Let us work out another numerical example on step bar. A step bar is of rectangular cross section and it is 30 mm thick. The first portion is 50 mm wide and 700 mm long. The middle portion is 900 mm long and it has a width of 50 mm at left end and 80 mm at the other end. The last portion is 500 mm long and its width is 80 mm. The bar is subjected to an axial tensile load of 50 kN at its ends. Find the total change in length of the step bar. E is equal to 120 kN per mm square. So it is a step bar having constant thickness. Throughout its constant thickness 30 mm. The first portion is 50 mm wide and 700 mm long. So width is of the first portion is 50 mm and its thickness is 30 mm. The constant thickness 30 mm throughout the step bar. So 50 mm is width, thickness is 30 mm. So it is having a rectangular cross section. The middle portion 900 mm long and it has a width of 50 mm at its left end and 80 mm at the other end. So it is width is changing from 50 to 80 and thickness is common 30 mm. So it is a uniformly tapered bar of a rectangular cross section. And the last portion is 500 mm long and its width is 80 mm. So the last portion, the width is 80 mm. So it's constant width and also thickness is 30 mm. And it's subjected to axial tensile load 50 kilonewton. So you need to find out the change in length. Let us tabulate the data. The load is 50 kilonewton or 50 into 10 raised to 3 Newton. Young's modulus is 120 kilonewton per mm square or 120 into 10 raised to 3 Newton per mm square. Thickness is 30 mm. Width of the first section is 50 mm. Width of the middle section varies from 50 to 80 mm. Width of the last section is 80 mm. Length of 3 sections 700 mm first section and 900 mm for the second section, and the last section length is 500 mm. Now this is a 3D view of the bar. So width is 50 mm constant for the first section, width is 50 mm constant width, and thickness for the entire bar, it is constant thickness 30 mm. So first portion is uniform area of cross section 50 by 30. So area you can calculate as 50 into 30. So uniform area you can use PL by A equation. The middle portion, the width is varying from 50 to 80. So it is uniformly varying and thickness is 30 mm. So it is a uniformly tapered bar and you have to use equation PL by T into B minus A into log B by A. The last portion, the width is constant 80 mm, thickness is 30 mm. So its area of cross section is constant and you can use PL by A equation. The area you can calculate as width 80 into thickness 30 mm. The length of each portion is given. So first and last section you have uniform area of cross section. The middle section you have uniformly tapered bar of rectangular cross section. The middle section, the area of cross section is uniformly changing. Now the first portion you can find out the change in length using PL by A equation, where area A1 is W1 into T. W1 is 50, width is 50, thickness is 30 mm. So 50 into 30 is area, Young's modulus 120 into 10 raised to 3, load is 50 into 10 raised to 3, length is 700. So it works out to 0.1944 mm. For middle portion, you have to use expression for uniformly tapered bar. So P2L2 divided by Te into B minus A into log B by A. P2 is the same load is acting in all the three sections. P2 is 50 into 10 raised to 3. L2 is 900. Thickness is 30. Young's modulus is 120 into 10 raised to 3. And B and A you can substitute that width at both the ends 80 minus 50 and log 80 by 50. You can also interchange A and B. You can write 50 minus 80 and here log 50 by 80. So elongation of the middle portion you will get as 0.195.